Hello again. Before we see processes in virtual memory, let's talk a little bit more about control flow. There'll be some special things about control flow that's going to be useful to implement process abstractions in virtual memory. Okay. So if you recall, processors do one thing, right? They execute one instruction after the other from startup to shutdown. Okay, so the CPU simply reads and executes a sequence of instructions one at a time. Okay, this is what we call control flow. Okay, so from startup to shutdown, we execute one instruction after the other. This is control flow. Okay, so how do we change the control flow? Up to now, we saw two ways. First, we saw jumps. When we saw assembly programming, there were jump instructions that changed the control flow. We used that to implement things like loops, conditionals, like if, then, else, etc. And we also saw call and return, which is used to implement procedures. Okay, it's used to implement procedure calls and so on. And both of these changes of control flow, they react to program state. They're part of your program, and they react to the program state. Okay. So, but the processor also needs to change the control flow to react to changes in system state, not program state. Okay. So by changes to the system state, I mean things like, what if the user hits Control C at the keyboard? Somehow the program has to be interrupted, right? And if the user clicks on a mouse, or like me, I'm using the pen here to write on the slide, I'm changing the system state, and there's a program, in this case a PowerPoint program, is reacting to my pen touching the tablet here. Okay, so these are all things that are external to the program. They're part of the system state. Somehow the program has to react to it. And the way the program reacts to it is by changing its control flow. Okay, other examples are when data arrives from the disk or the network adapter, somehow the program has to go and read data from the network adapter and the disk and to process it. Okay, and also there's things like if you do division by 0, something that's undefined. So somehow the program has to do something in its control flow to deal with that situation. Or if the system timer expires, from time to time. In fact, there's this device called the timer, the real-time timer in your system that from time to time it interrupts the processor to tell it like, hey, certain amount of wall clock time has passed. And this is going to be useful to implement context switches that we're going to see later in this module. Okay. But now the real question is, can jumps and procedure calls implement this? Well, it really can't, right? So they're not sufficient. We need systems for exceptional control flow for things that are not part of the program state. So the way we implement exceptional control flow is by using what we call exceptions. Okay? So an exception is transfer control to the operating system, okay, in response to some events. For example, some change in processor state. So here's how it happens. Okay? So say our user process is executing our code, and then this is the current instruction being executed. And then when a certain event happens that leads to an exception, for example, you have a division by 0, or you have something called a page fault, or some I/O request completes, or even when you type Control C in your keyboard, so the program gets interrupted, and then an exception happens, okay, and the control is transferred to the operating system. Okay, so and this exception processing in the OS is done by the exception handler. Okay, the exception handler is nothing more than a piece of code in the operating system that handles what should be done when a certain event, as an exception happens. Okay, and whenever the operating system is done with processing that exception, it returns to the instruction that was being executed by the user process. It could either return to the current instruction, it could return to the next instruction, or it could even decide to simply abort the program. So an important question here is, how does the system know which exception handler to execute? Well, that's going to depend on the exception that happens. So and there's something in your system called interrupt vector that all it does is it maps the exception, in each exception has a number, to the code that handles that exception. So it's not, so the interrupt vector is just a table that's indexed by the exception number, and the contents of this table is a pointer to an instruction that to the first instruction, the block of code that deals with that exception. Okay, so it's an indirect jump table. Okay, great. So and the way we do this, well, each type of event has a unique exception number. okay? And that's a number k, and this k is an index to the exception table, also known as interrupt vector. Okay? So, and then this handler is called every time a certain exception is executed. So whenever exception k happens, the handler k is executed. Okay, so there's two types of exceptions. The first time, the first type is an asynchronous exception, also known as interrupts. And the reason they're called asynchronous, it's because they are caused by events external to the processor. Okay, so and they are indicated by setting the processor's interrupt pins. So the processor, right? As you saw, there's a bunch of pins in the processor. Some of these pins are we call interrupt pins. So whenever we put a signal in this interrupt pin, something happens inside the processor. Okay? So an exception is raised, and then the processor jumps to the piece of code responsible to dealing with that interrupt. For example, this interrupt could be time's up in the timer, okay? Or it could be the mouse click and so on. Okay? So, for example, it could be hitting the Control C on the keyboard. As I said, just clicking on the mouse button or touching the touch screen like what I'm doing right now. A packet arrives from the network and so on. Okay? So now the other type of exceptions are we call synchronous exceptions. And synchronous exceptions are caused by events that are triggered by executing an instruction. When the instruction does something that's undefined, that's potentially bad. And there's three types of synchronous exceptions. One is called traps. It's just an intentional way of transferring the control flow to the operating system to perform some functions. In fact, that's effectively the operating system API. A trap is a way of an application to transfer the attention to the operating system so it can do something for the application. Okay, well, we call that system calls. Okay, so that's the operating system API. But there are also other types of traps. Whenever you're using GDB, when you insert a breakpoint into your code, it adds what we call breakpoint trap. So your code executes. Whenever it reaches this breakpoint, it sets a trap. It diverts execution to the debugger. Okay, and so on. Okay. Great. So, and the traps, they return control to the next instruction that called the instruction after the one that caused this intentional trap. The other type of synchronous exceptions that we call faults. These are unintentional. It was not the intention of the program. Okay. But they're possibly recoverable. For example, if you have a page fault, which you're going to see more detailed in virtual memories, when the program touches a piece of memory that is not actually in memory, that's a fault, and the control is transferred to the operating system to deal with that situation. Okay, we're going to see an example on that a little later in this video. Okay. So, or we have a segment protection fault, which you might have seen seg fault when executing some of your programs. That's exactly what happened. Okay, so you might have touched a piece of memory that's undefined, and then that's unrecoverable, so your program is aborted. Okay. Another example of a fault is when you do division by zero. Since division by zero is undefined, that leads to an exception, and your program might have to deal with it. It can potentially be unrecoverable. Okay. So, and in the case of a fault, the program either re-executes the faulty instruction, or the program aborts. Okay. Finally, the last type of synchronous exceptions we call aborts. They are unintentional and unrecoverable. Okay. One example is when you have a parity error or a machine check that happens because an instruction touched something that is bad in your system. Okay. And it just simply aborts the program because it's just unrecoverable. So now let's see an example of a trap. Okay, an example we're using it to transfer control to the operating system. Okay. So opening a file requires an operating system service, okay, and that's going to be done using a trap. So, for example, every time your program opens a file, eventually it's going to call this open function that takes a file name as a parameter and then some options on whether the file is for read, write, or both. Okay, and if you look at the assembly code for this function open, you're going to see this instruction here, int hex 80. Okay, so this diverts, this int is a trap that diverts the execution to, so your process executing here. So in this example, your program is executing whenever it reaches, it executes int. It's as I said, it's an exception, it's a trap. Controls transferred to the operating system, and the operating system knows based on the number that it needs to open a file. So it opens the file, and returns to user code so you can go ahead and manipulate the file. Okay? So, and what DOS does here is it has to find or create a file and get it ready for reading or writing. Okay? And then it returns a file descriptor, so that's why there's a pop here. Okay? Now, another example, this is an example of a trap. Let's look at an example of a fault. Okay? Remember that a fault is an asynchronous exception that happens due to something that an instruction does. Okay? So let's see what happens here. Say that you have this piece of code here. Okay, so eventually we're going to touch memory. And now, so the user just writes memory location. And if it so happens that if that portion of the user's memory is currently on disk, it's not in actual memory, okay, you're going to see that in more detail in virtual memory, but it could happen that whenever you touch a memory location, the memory actually isn't there yet. So we have to transfer control to the operating system to actually map that page in. Okay, so here's our instruction that's being executed. Whenever you execute that instruction, it could be that if it so happens that the page is not in memory yet, this leads to what we call page fault exception. Okay, that transfers control to the operating system. That's going to create the page and load it into memory. And whenever that's done, it's going to go back and note that now the difference is that it's going to re-execute the memory access because now the page is there, so we can go and actually execute the memory access. Okay, so in this case, the page handler here that's executed by the operating system loads the page into physical memory and returns to the fault instructions. So move has to be executed again. Okay, so and hopefully the second time is going to be successful. If you could map the page. Now, if you touch a bad memory location, like let's say you just have a pointer problem. Okay, you just had a pointer problem in your code, so that could be an invalid memory reference. So in that case, if you touch a piece of memory that's not mapped, but the OS cannot find the operating system cannot find a valid mapping, it has to abort your code. Okay, the execution of your program. So let's look at this example again. We have our move instruction here. The program is executing. It reaches the move instruction. And then that leads to a page fault because it's unmapped. But the OS determines that, you know what, not only it's unmapped, but this address is invalid. So what it needs to do, so it just had to go and signal the process, say like, unfortunately, I'm going to have to abort you. So it sends this zigzag fault to the user process, and the user process exits with a segmentation fault error. Okay, so now, to summarize, exceptions are events that require non-standard control flow. That means that not with jumps or call, okay? Typically generated externally in case of interrupts or internally in case of traps and faults. And the exception is handled by the operating system. And when the operating system handles that exception, one of three things could happen. It re-executes the current instruction in the case of, for example, page faults. It could resume the execution with the next instruction. That is the case of doing a trap and using operating system services like opening file, reading, or writing to a file. Or it might choose to abort the process in case the exception is unrecoverable. See you soon.